yesterday. What was the x-axis called again? Polar axis. Good. And what's the y-axis called? The pi over 2 line. Oh, interesting. So if something in polar mode has y-axis symmetry, it's called pi over 2 symmetry. And if anything has x-axis symmetry, it's called polar axis symmetry. And if anything has origin symmetry, it's called, what's the origin called? I said it yesterday. Awkward, we need to learn in BC. What's the origin called in polar? Remember, concentric circles, latitudes and longitudes going out. What's here? The pole. Alright. Letter A. For what number? Whoa, there's work to be done? Oh, that's fun. For A, we have 2 points, 2 polar points. Letter B, we have some other polar points. Wait a minute. Oh, cheaters! They just wrote tangent inverse and didn't go to their calculators? So it was supposed to be by hand. And do you guys know tangent inverse of 4/3? It's not unit circle because unit circle is square root of 3 over 3, 1 square root of 3, 0 and undefined. Other than that, 4/3. But -5 is going the opposite direction. So what did they do to the angle? Pi plus would throw it in the opposite quadrant. There is a way to deal with angles that you do not know without your calculator. And letter C, some more polar points. Is there a letter D too? I feel like there is.
Oh. There should be.
Awkward. All right, letter D. It's okay. I got you. Letter D is the point 2, 0. Okay, well, that's kind of easy because the point 2, 0. Wait, is that a rectangular coordinate, right? Choop choop. 1, 2. Buckle my shoe. 3, 4. Couldn't you just do 2, 0 because 0 is an angle and 2 is a radius? Oh, that's fun. What could you have done if your angle was pi? -2, because pi would be over here. We would have to go the opposite direction, right? What could you have done if the angle was 2 pi? I mean, there's not a lot more to do besides 3 pi, 4 pi, 5 pi, -pi, -2 pi, -3 pi. That's kind of all you've got. That's more than enough. Are we okay? Any questions on number 4? This is going slow. Let's pick it up. Okay. Number 14. You just had to see if you could make your graphing calculator graph it. You were what?
I was so mad because I started doing the table until I realized I forgot how to do it with my calculator. So I started doing it with.
Oh, instead of just going polar mode and then putting it in? Oh, yeah. Polar mode, putting it in. And guys, polar mode, we no longer have T-min and T-max. Now we have, did you guys look in your windows at all? Now we have beta-min and beta-max. T-min, T-max is for what types of functions? Parametric. Beta-min, beta-max is for polar. Number 25, you guys were just doing a quick conversion. It's a circle. Or maybe it wasn't a quick conversion. Anybody get confused by, was it r equals 1? Oh, no, it was r squared. They were nice. If it was r equals 1, it'd be a little bit harder. But. Number 36 was an ellipse. Maybe you recognize the equation. Because it would have actually, I don't know about you, for me it would have been easier to graph by hand, I think. Oh, I guess if you threw it in your graphing calculator, it wouldn't have been that big a deal, I suppose. Okay, maybe it'd be easier to throw it in your calculator. Number 72, what was going on there? I feel like that was a weird one. Was it a weird one? Number 72 gave you the following direction. Yes, I was trying to challenge your brains. You need it every now and then. Look, extending the ideas. Okay, so show that the distance between 2 points, r1, theta 1, and r2, theta 2, in polar coordinates is. And that was it. You're welcome. welcome. Now, some of you saw the answer key, but that might not give you much direction. Did anybody think of anything to do? Lorenzo? Law of cosines. Because law of cosines says, or what does the law of cosines do? Maybe that's a better way of saying it. Can I just do an arbitrary R1 theta 1? Is that okay? Oh, awkward. You can see like my cuticles, which are not so hot. How about there? There we go. Okay, so we have R1 theta 1. I guess we'll end it somewhere, yeah? And then we have, why not? Let's just have R2 theta 2 be bigger for sake of argument. We're trying to find the distance between them? Why did Lorenzo say law of cosines?
If you're given two sides and an angle, you can find the third.
Isn't law of cosines for some arbitrary, not necessarily right triangle? And doesn't it let us take things like angles? I should have used, I don't know why I'm using Greek letters. I mean, I know why, but that's okay. We'll call it A and B and C. And law of cosine says to find, in this case it'd be kind of like finding this guy. A squared is equal to square root of B squared plus C squared minus 2BC cosine of A. Ooh, remember him? And it would let you find the length of a side given the length of the other two sides and the included angle. Oh, square root. Sorry. Yeah. There you go. I put the square root in. That's my bad. But yeah, we could have done law of cosines. That's one way. If you had drawn a picture and realized it was really not necessarily right triangle, so we have to use not Pythagorean theorem, but we can use law of cosines. But you would have to do theta 2 minus theta 1 to get the included angle right here, because we only want this part. But isn't that what this ends up being? Oh, it's hidden. Subtraction of the two angles, and then you have the two sides, and then the two sides. But what if you didn't know it was law of cosines? What's the way that the book did it? How do you find the distance between 2 points? Distance formula, D equals the square root of x2 minus x1 squared plus y2 minus y1 squared. But we don't have x's. What do we have instead? R's. Isn't there a formula for what x equals in terms of r and theta? So what did they do? They had fun and they said, well, x2 must be r2 cosine theta 2. x1 is r1 cosine theta 1. y2 is r2 sine theta 2. y1 is r1 sine theta 1. And then they said, well, if we were to actually FOIL all of this, him squared minus 2 times him plus him squared, and then similar for that guy as well. Then they had to go ahead and there are some positives and negatives that would cancel out or that would combine. And then there was some cool, I think it was sum to product? No, composite argument properties from those really old trig properties, the big old huge page of cosine A plus B is cosine, cosine, look together. Cosine A, cosine B, cosine sine change, plus sine A, sine B. Anyway, you have to remember a lot of trig. Long story short, what's the easiest way to do this? Law of cosine way. Yay, good job, Lauren. But their way would have eventually worked. You would have just had to use some canceling out and then some trig properties to get this composite argument, which would have been a bit of a mess. I think that was it, yeah? Okay. So what do you guys have questions for on this section for me, odds or evens? I don't care. Anything? Yeah, Gina. 39. What else? Lainey. 25. What else? 51. 61. What else? 29. 29. Okay, let's start with these. And if you guys are like, I'm bored, maybe you should be highlighting important formulas in your notes and studying them for tomorrow. Wait a minute, important formulas in our notes that aren't in our forever cards? Shock. Horror. What's going on? I feel like maybe, just maybe, we should maybe start some endeavor cards. What do you guys think? Because polar parametric, even though we won't be coming back to them until the very, very, very end of the year, that does not mean that if we have a quiz tomorrow, we shouldn't memorize some formulas already from, pre-calc. But in order to find those endeavor cards, I should probably go back to last year. So let's go ahead and go here. And let's go ahead and go here. Because I think we only need the first slide and the first endeavor card. And here, and here, and here. Alright, we are officially starting in our class notes shared folder our endeavors for 2019-2020. Did you guys see that your forever cards are loaded in your folder? Yeah. Careful, they're your forever cards. I wouldn't necessarily give them to Calculus A, B, and say, here, write the whole thing down and be done, because remember how we changed a few things last year? Okay, just a quick heads up. I also want the title card. There we go. If you guys notice, I didn't necessarily put down parametric because I don't necessarily think there's anything with parametric you should memorize. Let me get rid of this. Sorry, that's annoying. Beep. I don't think there's anything with parametric you need to memorize, at least in a forever endeavor kind of fashion. I think polar are the ones that are more confusing. And if you notice, I do have this whole x equals r cosine, y equals r sine. And basically, they all come out of this right triangle. And remember, these are not the only formulas. We could do secant, we could do cosecant, we could do cotangent, we could do other things. These are just the basic ones. I'm going to freeze the screen so you guys can get this down. I'm going to take a picture and put it in your notes so that we have this documented. Endeavor number 1. I would, because you have to do title cards again. Unless you want to start from the front and always study backwards. It's up to you. As long as your title's on one side, info on the other, it's up to you as to which way you want to start. I did give an idea to AB this year, though, because starting backwards is kind of annoying. Unless you cover the front and the back, and so you don't really know which one's front or back. Like some of you guys cover your composition books to make it look cool. You could cover your forever card flaps, and then you don't know. Or you even redefine it to be like, ha, this is the front, and that's the back. But up to you. Meanwhile, I'm getting set up for number 25. That was our first question. Number 25 was a conversion question. Yes, a conversion question. R equals. Ooh, not that marker. Nope, 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 nope. Nope, nope, nope. Where's my nice marker? Ooh, that's a nice one. Okay. You guys almost there? Number 25 gives us, I'm switching over in about 30 seconds, R equals 5 over. Now normally, once again, I would have you guys up to the board because we would be speeding through these questions, trying to get to the next section, the next topic, etc. But we're doing this because we have a quiz tomorrow. And I don't specifically have a quiz review. Now, guys, do each of the chapters, Chapter 1 and Chapter 11, do they have test reviews? Yes. Could you look through and find specifically the parametric test review questions and the polar non-calculus test review questions? I suppose. Or you could theoretically just pick random homework problems to go through and try again without seeing the answers and the solutions and the corrections. It's up to you. The most important thing, I think, is have the formulas down. John?
Are we turning in our notes and homework for this case?
Yeah, but you'll probably have them back by the end of class. I'll just do them fast. Because you only have like 2 sections. Yep. So give me what you already have because you guys are amazing and you do it every day in class. All right, so awkward. Ready, set, let's talk. Ooh, that's bad. The directions, I'm trying to get it to zoom in. Yikes. No, webcam, I'm right here. Nothing? Nothing at all? Okay, the directions for number 25 are replace the polar equation with an equivalent, aka eliminate the parameter. You guys get that directions as far as Cartesian means eliminate the parameter, go from polar to rectangular, right? And then it says identify or describe the graph without using a grapher. So your goal was to do this without a graphing calculator. There he is. Good morning. Okay, if I were you guys, you have multiple options. You really do. My preferred method, though, because you have no idea what you're going to see tomorrow as far as a polar equation and how to convert, would be just to think of your right triangle with theta and x and y and r. What could you do as soon as you saw sine? Can't you go over to the triangle and say, I know sine. Sine is opposite over adjacent. No, sorry, opposite over hypotenuse. What could you do for cosine? Same thing, except this time it's adjacent over hypotenuse equals r. How do we simplify a complex fraction? Yeah, can't we multiply by r over r? And so wouldn't we end up with r is equal to 5r all over y minus 2x? Then couldn't we multiply up and divide down and rearrange that a little bit to get y minus 2x is equal to 5r over r, which ends up being y minus 2x is 5. Isn't that a linear function? Dun, 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 dun. But what was another way? Because there were other ways. Yeah, you could multiply this to the other side. You would have distributed r sine theta is y, r cosine theta is x, and you would have gotten the exact same thing.
Using the equation, does the x and y have to be on the same side?
This is standard form, so technically it's okay. I mean, I guess the better standard form would be negative 2x plus y is equal to 5. You could technically have gotten that to slope-intercept form, so y is equal to 2x. Like, you could have done it different ways. I just stuck it to the man. Yeah, so matching with the back of the book, I just say make it match. AJ.
When you're eliminating the denominator of r,
Yeah.
you don't do it to both sides for that? Or
Well, I was multiplying by 1 creatively. So it wasn't like I was doing times r times r. Instead, I was just multiplying by 1. So I was doing like the complex fraction trick that we did in the summer packet for AB and MBC. Does that make sense? But if this is a little too complicated, or a little too out there for you, you could have definitely done what John said, which was just multiply that to the other side, distribute. It would have also worked. I just kind of saw the sine and cosine and said, hey, I have a triangle. I can do that. Number 29, is he another conversion one? Yeah, he is. And for number 29, it might be a good idea to think about what I just did for my trick, because number 29 says r is equal to 8 sine of theta. And so some of you are like, I can't get the sine over in a way that I'll get my r sine. Like I see r sine, I want r sine theta. It's a formula. But you could still go to your triangle and say, okay, whatever. It doesn't quite work the way I want it to work, but what is sine of theta? You could just say, oh, it's opposite over hypotenuse. And then couldn't you multiply? Now, AJ, here you go. I'm multiplying the r to the other side, yeah? So that one I'm doing movement. And I get 8y is equal to r squared. Isn't r squared just x squared plus y squared? Sweet. So x squared plus y squared is 8y. Kevin, in regards to your question, the standard form of a conic, we would put it all on one side. if we wanted to do standard form and not like complete the square and make it look all nice and neat and pretty. It's technically an ellipse. So if it was like pre-cal, I would have you guys go ahead and do like the whole x minus 0 squared plus y minus 4 squared equals 16. Is that right? Because you would add 16 and you would add 16 and you would complete the square. So that would be the standard form, but we're kind of just, I should say the clue form. But we're not really caring about that. We're just caring about getting some correct representation to match. Is that cool? 25, 29, we okay? Ish? Okay. And let's go ahead and go to, what was the next one? 39? And then 61. 39 is a slope question. Woo. Find the slope of the curve at each indicated point. So r is equal to, in number 39. How did you guys tackle this? Let me hear from you. You just derived it. You could plug in theta to find r, but the problem is to find the slope, I need to somehow do a derivative, yeah? The slope of the curve at each indicated point. If we were to do r prime, which I think some of you guys were saying you did, if we were to do r prime of theta, wouldn't that be dr d theta? The change of the radius with respect to the theta, right? And that would have been cosine of theta, and then we could have plugged in theta equals 0 or theta equals pi. But is this the slope of the curve? How'd that work for you? Wait, it's an odd. Odds are in the back of the book, even if we don't have calc chat. Hold on, pause. How did it work for you, taking the derivative and plugging in 0 and pi?
What if you didn't take the derivative but got the right answer?
Did anybody, I thought you guys, did no one take the derivative and plug in theta? Oh, did it work?
Yeah, I did. Yeah, it worked. I don't know what the answer is, but say I know that.
Lorenzo, did it work?
Yeah.
Did anybody check the odds in the back of the book?
I did.
AJ, what was the correct answer for number 39?
-1, 0, and 1 pi. 1 comma pi. -1, 0, and 1 pi.
No, when did I see this?
Yeah, it's a slope.
When the angle is 0, then the slope is -1. When the angle is pi, the slope is
Thank you.
Oh, sorry.
No.
Wrong, but
What was the slope?
1.
Okay, so hold on. I heard someone say take derivative and plug in theta. Now, maybe it was only 1 or 2 or 3 of you, but still. We know how to take a derivative. Derivative is positive cosine. We could plug in 0, but question, what's cosine of 0? Not -1. True? What's cosine of pi? Not 1. Am I wrong or am I right? Okay, so Joe, you said at 0 should be -1 and at pi should be 1? Okay. So does this work? No. And here's the reason why. They weren't saying find dr d theta. They were saying find dy dx. We can't just say dy dx is dr d theta. The slope of the line is the change in y over the change in x. But we're doing polar. I know, but still. The slight change in radius over the slight change in angle is not the slope of a line. We need to find dy dx instead. So hold on. That's kind of awkward, right? Because how do we find dy dx if we don't have y and we don't have x? Okay, well there is a cool thing in polar mode underneath second trace that does have to do with dr d theta, dy dx, and okay, yes, but let's say we were supposed to do this without a calculator, because technically up here, I don't believe these are calculator problems. How could we convert this equation? We could square both sides because then we get r squared, but then wouldn't we get nasty trig stuff over here? So how about we just do what I did a second ago and we say that sine is equal to y over r. Yeah? And then can't we do something like, hold on. We could multiply both sides by r, but is it as nice as it was last time? R squared equals. What happens when you distribute this time? So we can make this x squared plus y squared, but what would this guy be?
That.
So now what's the struggle? Taking an implicit derivative of this guy. And even after we take an implicit derivative of that guy, don't we need to plug in an x and a y? How are we going to find an x and a y if all we have are thetas? Don't you guys have a forever card? And doesn't the forever card say, hey, you can get x and you can get y, right? So couldn't we get x and get y by plugging in x is equal to r cosine theta and y is equal to r sine theta? Well, wait a minute. Hold on. If we could have just done this from the get-go, maybe we don't have to take this super nasty derivative. Maybe there's another way. Maybe we could just do something like dy d theta, aka otherwise known as y prime of theta, all over dx d theta, otherwise known as x prime of theta. And would that give us dy dx? So, what is a way of doing number 39 that doesn't make us take a nasty implicit derivative and doesn't make us, well, do something horribly illegal? Plugging into x equals r cosine theta and y equals r sine theta, and then taking the derivative of each of these, and then plugging in the theta at hand and dividing them. Now, technically, this is something when we get into the calculus of polar that we'll do in a little bit more depth. But for right now, number 39. The best way to do this one is to go back to your Endeavor card and say, I know x, I know y, I need dy dx. I'm going to take the derivative of the y equation and the x equation when plugging in. Does that make sense? So what are you now left to do? A product rule and plug in theta is 0. A product rule and plug in theta is 0. And then put y prime over x prime. And then a product rule, plug in theta is pi. A product rule, plug in theta is pi. Y prime over x prime. And then you got it. If you wanted to, and I think we might have last year just because of this problem alone, technically you could take a peek ahead at parametric and polar derivatives. And realize that to find dy dx, it will be y prime over x prime, y prime over x prime. However, for my purposes, I think I might just save this until the end of the year for you guys and not make us go too crazy into it. Except for this homework problem showing you the idea of you have an x equals r cosine theta, y equals r sine theta. Put your r into the r spot. Take the derivative, and divide. And you have your dy dx. The other question that you guys asked was, I don't know, something weird. 61? Ah! True, false. Number 61 is a true, false. You may use a graphing calculator to solve. No, don't do that. There is exactly one point in the plane. You did exactly what I said, right? Y prime over x prime, Lorenzo? Yeah. There is exactly one point in the plane. Thank you, sir. With the polar coordinates 2, 2. Polar coordinates 2, 2. Is there any other way to get to 2, 2, guys? In polar? Radian would be 2, which is somewhere before 3.141596, somewhere before pi. Ooh, that was close. I almost got in my book. Then I go out 2. Is there any other way of getting here than 2, 2? Yeah, because in polar, couldn't we have gone the other way? Which would have been 2 pi minus 2, which is awkward, but hey, that totally works. Or I should say 2 minus 2 pi. That's the angle. That'd be another way of doing it. Or you could go, let's see, 2 minus pi with negative 2, because that would have put you in the fourth quadrant. You would have had to go back the other way. Anyway, sorry, there's infinitely many different ways of getting there. Because you could have gone the other direction, or you could have gone down and then gone backwards, or I know it looks like a rectangular, but what did they say it was? Polar coordinates. There are infinitely many ways of getting there. They just made it look gross because they didn't make it look like a nice angle. 2 radians? Ew, what is that?
There's exactly 1 point.
61.
Oh, they're not saying there's exactly one way of getting there. They're saying there's exactly one location. Sorry, yeah, there's exactly one location. It's right there. There's one place. But there's lots of ways of getting there. Sorry, I read it wrong. Thank you. There's exactly 1 point. There's one place right there. 2, 2 goes to one place, but there's infinitely many different ways of getting there, if that was their question, which it wasn't. Sorry, guys. I apologize. Okay, we went over the questions that you guys had. Is there anything else that you want to ask from the homework questions last night before I give you some very specific hints and clues about what to study for tomorrow? No? How about on the parametric homework? Anything that you guys needed to shore up and you weren't quite sure about? No? Okay. For tomorrow, you are going to want to know how to do the following without your calculator. How to graph a parameterized curve. We're saying that's how you say it. How to graph by hand a parameterized curve. Think back to your homework. How did you do that by hand? By hand. Table, right? A table with t's. How do you figure out what t's to use? Oh, sometimes you just had to make up t's. But the really nice ones, aka the quiz tomorrow, did what? Or gave you what? They gave you a beginning and an ending time, right? And you just picked some in between ones. So make a table. Use the t interval given. Find your x's, find your y's, but don't forget when you graph your points for parametric curves to show me what? Direction. Make sure to show me direction. What if I was to give you a parametric set of, well, a parametric set of equations? I can say that. What if I was to give you a parametric set of equations? I give you an x equals and a y equals. I give you a t interval, and I say, find the Cartesian equation. What am I asking for? Eliminate the parameter. I want you to get it in terms of y equals f of x. Now, it doesn't have to be y alone, unless you're needing to make it match. Unless you're needing to make it match. So you're graphing a parameterized curve. Can't do that. Show the orientation with a table. You are converting from parametric to Cartesian to rectangular. You're converting from polar to Cartesian using what? What did you guys just see me use on 2 different conversions of polars to rectangular? Triangle. But wait, there are certain formulas, like r squared is x squared plus y squared, ding. Or r cosine theta is x, ding. But what if you see something weird like cotangent? Draw the triangle and do the adjacent over opposite. The x over y, right? Okay. What if there was like a sine squared of theta? Doesn't match up with any of those formulas. Go to the triangle. What's sine of theta in the triangle? Y over r and squared. Go to the triangle. So if I want Cartesian, it means get to x's and y's, get out of r's and thetas, or get to x's and y's, get out of t's. Does that kind of make sense? Okay. I'm going to want you to graph a polar curve by hand. How do you graph a polar? 2 polar curves by hand. What did we do yesterday? It was the last 2 things that we did in our notes. Table. table with polar curves we need to be careful of. It's harder than parametric curves. What kinds of things will you put in your table? The nice ones. Because if you do the ugly ones, you better have the decimal equivalents down, or how else are you going to graph a poem? So if I were you, and I think in the ones I gave you, nice ones are enough. But to that end, can I give you a sample problem? A strategic sample problem? A very strategic sample problem? Can you graph the following? Polar has a Y, polar has an R. Go. You guys have time and you have groups. Get me a graph of that. What would the nice angles be for that?
If power of 4 becomes sine of 2, and sine of 2 is...
sine of 2 theta is equal. Alright, so it's going to be well,
because if it's 2, so if you do pi over 6, if you do pi over 6,
sine pi over 6, so 1 half.
what are we choosing?
And then it'll be 1 half times 3, and then it'll be 3 over 2. So that's you can't just do pi over 6, then it'll turn into a pi over 2.
Pi over 4? Why would you use that? Root 2 over 2 is gross.
Because the 6 makes it ugly.
I was thinking because 2 times pi over 4 is pi over 2, which is nice.
2 times pi over 6
Is gross.
is a no.
Oh, so then you went to the next one. Yeah, but 2 times pi over 4 is nice, right? Got it. Thanks, John. Now I'm tracking. I agree. I was just confused. Yes, pi over 4, normally bad, but plugged into a double angle. Good.
And sine pi is 0.
Start at wait, why did you start at 0? Yeah.
Everybody's back today, right?
Oh, well, just start at 0.
Maybe plug in pi over 2.
So we
If you
count
plug in
in
pi over 2
what
is
we
0,
the other
because
one.
sine of
So we're counting by.
Well, it's sine of pi.
Well, we can do. We can
Yeah,
do
pi over
maybe
pi over. Yeah.
What's it like?
Kevin, you're like.
And then it's like... How are you converting it?
If you put an I, it's already 0.
3 pi over 4 would make it so that 6 pi over 4.
It becomes 2
And
pi
then it would be 3 pi over 2. And then that would make R negative.
Sine of pi is 0. Pi is 0.
So counting for this. Oops, that was loud.
If you plug in pi over 4, it becomes pi over 2. And that's 0. Sine of pi over 2 is 1.
Wait, no, I can't.
I'm working on it.
Then pi.
I'm not kidding.
Then 5 pi over. Oh, yeah, 5 pi over 4.
Yeah.
Then 6 pi over 4. 5 pi over 4. 2 pi. If we're going to 2 pi. Fall to 0. Well, it seems we are because we're doing one of these. I would think. Now plug in. So which ones do we have? 0, sine 0 is
When you plug it
0.
in, that just becomes pi over 2.
R is 0. So
Sine
it's
of
just
pi over
1
2
is
is
right
1,
there.
so it becomes 1.
And then pi over 4 would make it so that it's pi over 2. Pi over 2. Yeah, it's 3.
So we would just need more points.
Sine pi over 2. Sine pi 0. 0.
Yeah.
Can I start playing?
Why? This is so weird.
plug it in, it'd be 3 pi over 2, and sine of 3 pi over 2 is negative. The second quadrant, you're right, but multiplied by 2. You have to plug in, and you have to multiply by 2, which is why we're using pi over 4s, because times 2 are pi over 2. We gotta keep track of who they are. So whenever you see one of these guys, the nice angle isn't so much, oh, sine is nice at pi over 6. No, but I have to multiply by 2. So 2 times what would be nice? What if it was a 3? 3 times what would be nice? Oh, pi over 6s. Yeah, I wouldn't mind pi over 6s. Wait, but that would reduce to 1 over 2. How about pi over 18? Because then it would become a pi over 6. Hi, guys. Play around. Practice. Polar parametric. I'll see you tomorrow.
Good.